Okay, so this is 12.4. You could measure an atom. You can. We talk about the diameter of atoms all the time. And what we measure in atoms, remember these are spherical objects, roughly. We usually represent them as little flat circles, but they're three-dimensional. If they weren't three-dimensional, neither would you be three-dimensional. And you are all three-dimensional, at a minimum. So when we measure atomic radius, this is kind of an odd little feature. We measure 1/2 the distance between the nuclei of identical atoms that are bonded. So I'm going to draw what that looks like. Whoops. Okay, they're the same, everything. Each of them have a nucleus. You know, now we're back to representing this as a nice set of little concentric circles. We know it's not. We know that the quantum model gives us the big fuzzy cloud of cotton candy. But that outer white line is representing sort of the outer edge of the electron cloud. So out to the edge of their electron cloud. We look at 1/2 the distance between these two. Okay? So if this is the total distance between those two things, we look at 1/2 of that, and that's what we call atomic radii. We'll get into later why it's important that those are identical atoms, but it is important because if they're not identical, they have different levels of attraction for electrons, and so they can influence one another's radius when they're bonded. So it's very important that this is actually identical. Every time I draw this, I want to put eyelashes on it and a smiley face. Just cause. Okay, so that's atomic radius. That's easy. Fantastic. Good. We've established. What there is to say is that as we go from group 1 over towards group 18, that radius tends to shrink. Okay, fine, whatever. It shrinks. I accept that. I accept that. Sure, I can memorize that. I don't want you to memorize it. I want you to understand why it happens. Because why it happens is also important in terms of how those atoms then behave with other atoms, how they work and play well together. So as we go from group 1 over to group 18, the radius, whoops, can't spell, decreases. And you're welcome to write atomic radius decreases with an arrow that way on your periodic table. It's useful. So, okay, sure, like I said, I can accept that, that's fine. Now here's the weird part though. If we're within a given period, so, let's say we're looking at period 3 here. Because we're in period 3. No, we're in period 4, never mind. Okay, I thought that was funny for a half a second. If we're in period 3, as we go from group 1 to group 18, what's actually happening to each atom, to each new element? It's gaining protons, it's gaining electrons. It's actually getting more stuff. How on earth is its radius decreasing? Okay, it would seem that they have to. The only way for that to happen, you're adding more stuff, it must be packed in more tightly. Okay, well, let's look at the other trend that exists. The other trend that exists is as we go down each individual group, so down group 1, down group 2, down group 13, down group 17, down group any of them, the atomic radius increases. They get bigger. Now that one kind of makes sense. What's happening every time we go down a period? Every time we go down one step within a group, what are we adding?
A new energy level.
A whole new energy level. So it kind of makes sense if we think back to that old Bohr model, the big concentric circle rings that you learned as a freshman. Okay, yeah, you're adding a whole new ring on the outside. It got bigger. But when we go across a period and we add more stuff, it gets smaller. What gives?
Is it because they're separated into, like there's, like in the S level, there's two D level?
Oh, because they're in separate orbitals. So you think maybe that has something to do with it? That's an interesting hypothesis. Anybody else got a hypothesis? Yeah?
Is it because they're getting closer to having a full outer shell?
Okay, is it because there are actually more of them on that energy level, they're getting closer to having a full outer shell? That's an interesting hypothesis. Anybody else? And there can be more than one factor. Very often when something occurs, there's more than one reason behind it. Other thoughts? Okay, so let's look at sort of a, we're gonna fall back to that old standby Bohr model as a graphic. We have an old sort of, this is a mock-up, it's a model of a Bohr atom. And let's first, whoops, let's first look at lithium. So let's draw the notation for lithium. I'm actually going to copy this, shrink it, set it aside, paste it, set it aside. I have to make this smaller. Okay, we have a hydrogen atom. It's got one proton. So in the center, I'm going to put one little tiny plus sign, one little proton. How many electrons does a neutral hydrogen atom have? Also one. Yeah. So I'm going to put one little, and I chose a horrible background. There's really no good way to do this. So I've got one proton pulling on one electron. These two things are attracted, right? Why? Opposite charges. Opposite charges are attractive to one another. These two things are attracted to one another. They're exerting an influence in towards one another. Okay. One pulling on one. It's not much of a game of tug-of-war. So we can go one, well, let's actually first, before we do that, let me set that aside. And let me go, I'm going to borrow this, copy it, paste it, and I'm going to make this helium. How would I make it helium? I need to add what? Add one proton, add one electron. So I'm going to add one proton. We now have two protons in that little nucleus. We now have two electrons. That's helium. So here, we've moved across the entire first period. When we move across that entire first period, we now have two pulling on two. There's more to get a grip on. So the radius for helium, even though helium's got more stuff, the radius is smaller. Because these protons can exert a tighter pull. Where were all my neon colors? The neons worked really well on here. So these protons can exert a tighter pull. There are more protons and electrons grabbing onto one another to pull it tighter together. Okay? So you get this increased attraction of opposite forces. Now, if we move if we do something a little bit different, and we go down to lithium. So now, instead of moving across a period, we're moving down a group. So we've gone from hydrogen to lithium. How many protons does lithium have? 3. Yeah, little 3-proton atom here. So lithium's electron arrangement, it's got 2 electrons on the first main energy level, and it's got 1 electron on that second main energy level. So it's got more stuff. Anybody here the youngest child of a large family? Okay. So I'm an only, I have nothing to relate to, but my husband's one of 2. And he has always said, every single thing I did, my parents were all up in arms about. They gave me all kinds of grief about. I was so monitored. They were so strict with me. David, his younger brother, did the same thing I did. They went, yeah, whatever. Like that, those first couple get a lot of attention. And with most families, maybe because of exhaustion, as you n equals whatever number of children gets higher, each next child in line may get a little bit less strict treatment. Things get a little bit looser. This is what I hear. I don't know. Like I said, I got no basis. That electron out on that outer energy level is that last kid. The supervision may not be quite as tight. They're just a little bit further from nuclear control. So that nucleus, though you've got 3 pulling on 3, that third one is out. It's shielded by another level, by another main energy level. So it's a little bit further from the nucleus. You know, the Schrodinger wave equations show us a 3-dimensional region that's just a little bit further out. And so this is called it's called electron shielding. I almost said nuclear shielding. No. It's called electron shielding. So those outer electrons are shielded by the inner energy levels. So they get less attractive force. So if we move, so as we go down a group, they get fluffier. They get bigger. Got a little demo for you.